Good morning. This will be a quick review of Chapter 4.2, which is What is a Machine? Discussing simple machines. Okay. When we're talking about a machine, we want to first remember that it's a device that makes work easier. And if we remember back to our 4.1 notes and we were defining what of the variables of work, W equals F times D, which of those three variables were the difficulty rating, we remember that it's force. So we want to decrease force by increasing the distance of the input. Right? So we're going to make the force less by manipulating the distance that the human aspect of the machine travels. And you'll get what I mean by that in just a second when we talk about work input and work output. I'm going to blow this up a little bit here. So work input is the work done on the machine. So the work the human does on the machine. Whereas the work output is the work the machine does on the object. So the work input is the work you are doing on the machine. So if you're using a can opener, it's you twisting that knob there. The work output is the work the machine does on the object. So that would be the can opener actually twisting around and cutting the top of the can being the object. Essentially, the machine is kind of the middleman between you, the human, and the object. So theoretically, work output should equal work input. This is what would happen in an ideal world or an ideal machine. And as you know from our conversation about Newton, the ideal world isn't exactly what would be perfect for us to live in, but is a world without gravity and without friction. So for work output to equal work input, there would have to be no friction involved in the simple machine, and that's just never going to happen. So what will always happen is you will put in more work than you get out. Work output will always be less. Output will always be less. Okay, we'll talk about a little bit more about why that's the case in some examples. So force distance trade-off is what we were talking about right up here. Right? This is your force distance trade-off. We manipulate the distance to make the force smaller. So I've got some pictures rather than drawing things because you know how terrible I am at drawing. So here is our lobster cracker, right? So imagine a lobster right here, right? So here would be your lobster, right? If we are going to use these lobster crackers, we're not going to grab them up here. We're going to grab the lobster crackers down here. And so we're going to close a distance of, let's say, 4 inches. And if we close a distance of 4 inches, and the lobster cracker up here where the lobster is closes 1 inches, we have a power of 4 times. Meaning that the distance differs by a multiple of 4. Distance differs by 4 times. So theoretically, the force will differ by 4 times. Right? A little bit of that will be lost to friction, so it'll be more like 3.9 times that the force will differ by. But in that ideal world, in a perfect world without friction getting in the way, all of that distance force trade-off would go right into a greater force by 4 times. So you could also squeeze the lobster claw with your hand and squeeze it that 1 inch, and you might possibly be able to crack it. But if you grab the lobster crackers down at the end here and close it 4 inches, you're going to get 4 times the force out of this tool than you would just by using your hand or by grabbing the lobster crackers up here. So to look at this mathematically, if work equals force times distance, without the lobster crackers, right, we're going to be closing the distance would be 1 inch that we are applying the force, right, if we grab them up top. And let's say the work is 4 joules, right? That would mean we'd have to apply a force of 4 newtons. If instead we are going to have 4 inches of travel, we can actually just put in 1 newton of travel. So see how there's a difference in force between these two of 4 times, right? That's in the ideal world. So you now only have to apply a fourth of the force because you're traveling 4 times the distance, which is much easier. In a paint can, if you are going to try to lift this paint lid, right, it might even lift maybe like 1 inch. But you, with your handle of the screwdriver, are going to start with it up here and move all the way down here. So let's say that's something like 6 inches. So if we move it, the tool, we move our end of the tool, the input end, 6 inches, and the output end moves 1 inch, that means that there's a 6 times difference in terms of the distance as well as the force, the input and the output force. So we will, through this tool, be able to apply 6 times the amount of force than if we were just trying to pry up this paint can 1 inch with our hands or by holding the screwdriver right here, for instance, which wouldn't make much sense. We want to hold the screwdriver as far back as possible, all the way back here, because that gives us the biggest range of motion possible. And the bigger the range of motion, the greater the distance, the less force we need to apply. The book talked about simple pulleys a little bit. We're going to talk a lot more about those in 4.3, but simple pulleys, they don't change the distance. They don't change the distance. And they don't change the force. They just change the direction. We pull down, the object moves up. It's not until you get multiple pulleys or movable pulleys that the distance and force actually start to be changed. But we'll learn more about that in 4.3. Last example we're going to talk about is the screw here. The screw is, if you stick it into the wood, it'll be about yay long. Let's call that 2 inches. But if we look at all of these threads here, right, that if we kind of like got rid of the actual screw itself, those threads would look something like that. If we straightened them out, they would actually be 4 inches long. So that's going to give us more force or more distance by 2 times, which means that the force we have to expend is going to be half. Right? Half the force because of 2 times the distance. So since the whole point of this screw is to get it stuck in the wood and hold the wood together, it's going to take a lot of work if we don't have such long threads. If the threads instead were just, there were 2 threads like that, we're going to have to turn a lot more because the distance is going to be shorter and it's going to be harder work on the screw than if we have all of these tiny little threads. Theoretically, to make it even easier, we could add lots and lots and lots and lots and lots and lots and lots of little threads, which would increase that distance traveled even greater and make the force that we have to apply even less. So if we work back up here to the notes, we've covered all of these just down below. So to talk a little bit about mechanical advantage, that's the number of times the machine multiplies force. So that's what we were figuring out down below when we were looking at the distance. For us in the classroom, it's a lot easier to measure the distance that the screwdriver and the paint can travel than it is to measure the force that you push down on or the force that the screwdriver pushes up on. So for our purposes, since we don't have very high-powered force meters, we can measure the distances traveled much more easily and then apply that information to the force. So this is the number of times the machine multiplies force. So this basically tells us, in layman's terms, kind of in everyday terms, how much easier the machine makes the work. Okay? How much easier is it going to be? With that machine, how much less force do you have to apply? Now, mechanical efficiency is very similar. It tells us something a little bit different. So it's the ratio of work input to output. So here, we're talking about force, right? So that would be output force divided by input force. But here, we're talking about work input. So work output divided by work input times 100. And the reason we multiply it by 100 is to get it into a percentage. So this really tells us the amount, and really the percentage, of work lost due to friction. So in any of these cases here, whether it's with the nutcracker or the screwdriver, a little bit of energy is going to be lost overcoming friction. And that friction could be expressed as noise, it could be expressed as heat or light, or a little bit of scraping feel that you have when you're using the screwdriver there. All of that is friction, and all of that is wasted energy that actually doesn't help you achieve the work that you want accomplished, meaning lifting off the paint can or cracking the nut or the lobster. So that little bit of work that is lost there, even though you're trying to transfer that force, can be calculated with mechanical efficiency. Remember, the ideal machine doesn't exist because of friction. Let me know if you've got any questions.